Assalamu alaikum. This is Dr. Ali Mughebel. And now we look at ARQ, Automatic Repeat Query Systems, and with a focus on satellite communication. The requirement for retransmission is very important for satellite communication, especially that we have long delay. So we have three main types of ARQ systems: automatic repeat request or query, and those systems, some of them require memory, buffer, and then we have to look at the delay and addressing and so on. There are three main types of ARQ systems: stop and wait, go back in, and selective repeat. Our objective is not to spend a lot of time explaining them. There are lots of excellent videos that explain these, but we'll just shed some light on them. And as I said, we will focus on how they relate to satellite communication or long delay communication. We'll have three examples, numerical examples. In fact, we'll have one example, but we'll solve them for the three different categories. So let's look at stop and wait, the first one. Stop and wait, this is the time axis, and here is the transmission reference, and this one is the reception reference. So we transmit the first packet. It takes some delay, so it will arrive here. This is TD, the transmission delay. Once the packet is received, we get an acknowledgement. We don't start sending the second packet or the second group until we get acknowledgement, and this is the name stop and wait. So transmit and wait until you get an acknowledgement. So we have the round trip delay, and you can tell that for satellite communication this is going to be much greater than the transmission delay because of the long distance usually. And we get to send the second packet, it gets received. If it is an error, instead of getting acknowledgement, we'll get a negative acknowledgement, and of course we will repeat the transmission. So there is no problem here of receiving the packet out of sequence or so. There is no large buffering requirement because everything that we receive can be sent to the destination. They receive in sequence, they are received in sequence, and there is no requirement for ordering even. Now if you go for go back in blocks, in that case we will keep transmitting, and we will be sending blocks. So I will send the first, the second, third, and fourth, and so on. I will have a certain sliding window, and the sliding window size is going to be n. So it could be 3, 4, 5. So I will be transmitting 4, for example, if n equal to 4, or 5 if n equal to 5. And then I will wait for, they will send the first one. I will not wait, second, third, fourth. And of course, then the acknowledgement will start to be received. Whenever I get a negative acknowledgement, I'll go back, drop everything, and transmit again. So we have 2, 3, 4, 5. So we are transmitting not just send and wait, instead send n, and then send n until if you get an negative acknowledgement, then you have to retransmit. So you have the transmission delay. If a block is received in error, then we just don't send that packet only, we send the entire window again. Now for selective repeat, a buffer is needed. Now we have to store things because things could be out of sequence. A buffer is needed at both ends of the link, transmitter and receiver. And of course, this is to ensure blocks are sent from the receiver to the transmitter, from the transmitter to the receiver in the correct order. Of course, this is going to introduce latency. So there are pros and cons of each. For example, here we'll be sending 1, 2, 3, 4, and whenever there is something is not received properly, we have negative acknowledgement. I will only retransmit number 3. That's selective repeat. I will not transmit everything again. So 4 will not be transmitted. But now you can see that things are now out of order. So we need to store them and then, of course, arrange them and get them to the destination. So these are the fundamentals: stop and wait, go back in, and selective repeat. If you need to, as I said, if you need to know more about them, there are lots of videos that explain these in a long time. Our objective is just to recall them and know the basics. So we'll learn more about them in the examples. Okay, so the first example here says, calculate the frequency of transmission, throughput, and buffer. I colored these with different colors, just these are the requirements. calculate the frequency of transmission, retransmission, throughput, and buffer requirement of a satellite link capable of carrying data at a rate. We're just trying two different numbers. We'll color the first one with blue and then with green to get some conclusions. 24 kilobits per second. These are relatively low numbers, but the idea is just to get used to the concept. And then, of course, we are told that the block length or the packet or the group transmission is 127 bits is used, and the one-way path length is 240 milliseconds. That's like a geostationary satellite. So we're giving the block length, and we can get the transmission. Okay. For the link to be studied, the probability of error is 10 raised to the power minus 4. So now we will assume that we are using coding, and that code is double error correcting code using ARQ schemes, double error correcting codes, which means one single or double errors are corrected. We would like to study those three things for the three scenarios: stop and wait, continuous transmission with the transmission buffer go back in, and continuous transmission with buffer off at both ends, which is selective repeat. Fantastic. So we have three cases. We have multiplied by 2. That is 6 cases. And for each one of those, we need to get 3 outcomes. So in this slide, I will just continue finding the common information. And then we have 3 slides to cover each one of these, A, B, and C. Fantastic. So the probability of detectable error is 1 or 2 errors. So this is the formula that we find to count the probability of a given k errors. So for k 1 or 2, we need to sum the two numbers. So 1217 is the block length. This is for the case of 1 error, so k equal to 1. All right, and n is 1. N minus 1 would be 126. And plus the case of double errors, we have, this is the permutations, 127 choose 2. And then we just plug in the equation, and we got the probability of detectable error is 0.1262. Other than that, the error will not be detected. Okay, so the first question is, what's the frequency of retransmission? Of course, the frequency of retransmission requires detectable error, and the frequency is the inverse of the probability here. So we have 1 divided by 0.1262 give you 79.24 approximately. I'll be using some rough numbers here. So we have 1 in every 79 blocks has a detectable error. Okay, approximately 1 in every 79 blocks has a detectable error. Now let's focus on the first scenario, solution for stop and wait. For the case of stop and wait, the time for sending and waiting for an acknowledgement will be the transmission time plus the round trip delay. So it's going to be 127. This is the transmission rate, and plus the round trip delay, 2 times 240. So that should give you 0.4853. I'm using blue here, and I'll be using green for the case of 1 mega. This is dark, the rate, and this is the time, lighter color. For the case of 1 megabit per second, we got the transmission time. Notice the round trip delay is the same. So we got 0.48127. You can notice that these two numbers are relatively very close. Why? Because the delay or the time is dominated by the round trip. It's not the transmission time. So this is the big number. These are the small numbers. So the throughput is almost the same in the two cases. We are sending, in the first case, 1 over 1.4853. Okay. This is for 1 packet or block, and which is almost equal to 1 over 0.480, which is almost equal to 2 blocks. Of course, you can be more accurate. I just want to show you that if you are going to use stop and wait, you will be dominated by the round trip delay, no matter how much you increase the data rate. So the time is dominated, as I mentioned, by waiting for an acknowledgement, whether positive or negative. Now, 2 blocks, this is the rate of transmission, 2 blocks per second, and the block is 127 bits per block. So this block cancels, we get almost our transmission rate is, or throughput if you want to call it, is 254 bits per second for both rates. This is really low. Now after 79 blocks, which is equivalent to 39.5 seconds, we detect one error in the average. Okay, this is to give you an idea about our transmission rate and our error rate transmission requirement. Why? Because we're sending 2 blocks per second, so this is almost half of that. Now we go to the second solution, which is we want to avoid the problems with stop and wait. We're going to go back end solution. Now the time to send the 179 blocks of 127 bits, we have 79, this is the average transmission, we have 79 times 127 divided by the rate, which give you 0.418 seconds. So the time required to send the blocks is 0.41. This is similar to the numbers we had before. Now if you receive negative acknowledgement, okay, for negative acknowledgement, which requires also a delay for transmission, a 2 round trip delay, 2 times 0.24 seconds, that's the round trip delay. And if you ask me how much data are we transmitting, are we losing during this, it's going to be 25 kilobits per second, divide by, if you want just the kilobit per second, if you want to get it in blocks, you divide by the number of blocks or bits per blocks. So they give you 91. So during the negative acknowledgement transmission, for the negative case, we get forward and backward. That's going to be, so we have sent all of these. There is no, on the average, of course, 79, there is no error. But now we send one with error every 79. So we get 91 blocks. We sent 79 and we lost 91 because the moment we get negative acknowledgement, we have to go back. We lost all this duration from 2 to 2. This is all going to be dropped, which is equivalent to the round trip delay of the negative acknowledgement. So we will need to discard this 0.48 seconds, which is 2 times 0.24. Now notice that the numbers they look similar, but they're not the same. This is the round trip delay and this is the transmission for 79 blocks. So the throughput, we send 79, which are correct, divided by the total, which is 79 plus 91. This 91 is the requirement for the dropped because of negative acknowledgement. So we get 0.465. This is the efficiency of our system, if you like, 46.5%. Okay, so if you look at the original transmission rate, it's going to be 24 times 0.465, and we get 11. Although we're transmitting at 24K, but because of the retransmission, the effectiveness is only, the throughput is only 11.2 kilobits per second. Now, the transmission buffer requirement, the transmit buffer must hold for 0.48 seconds of data, which is equivalent to, this is of course the transmission rate, 11,600 bits, because all of these will be retransmitted again. So this is a transmit buffer. For the case of 1 megabit per second, of course the received always going to receive things in the right order. So for the case of 1 megabit per second, I'll just change the numbers here, 24, 24. I'll get the same answer repeated, 79 times 127, but now divide by 1 meg, which is equivalent to 0.01 second. Okay, so now basically the transmission time compared with the round trip time is much smaller. So the amount of blocks that are going to be wasted is much, much more, because we could have done better rather than going back in. So when we wait 1.48 seconds for the transmission, we can find that in terms of bits or even in terms of time. So the buffer requirement is 1 meg times 0.48. This is the repetition of what we had before. This is now written in terms of 1 meg for the case of 1 meg. Okay, so this is the same equation we had before. I need now to store 490 kilobits instead of just 11 kilobits. That's much more requirement. And of course, the rate of transmission will be 1 mega, but now the effective, because the only effective time is this. It's 0.01 divided by 0.01 plus 0.48. This is the effective time. We can find that in terms of bits, but it suffices to find it in terms of time. And that reduces from 1 mega to only 20.46 kilobits per second. So you can see that for satellite, the transmission is really dominated by the round trip delay rather than by how fast you are. Okay, so we mentioned here that for the go back N, the throughput will be reduced, and there is also requirement for the buffer at the transmitter side. Now the last important type is the selective repeat. Of course, only lost blocks are retransmitted. So the throughput is going to be 78 divided by 79. We don't waste others, which is 98.73. The average data rate now is dramatically improved. The reduction is only 24K to 23.7 kilobits per second due to retransmission. But the buffer requirement, I need to store all these data because I could get negative acknowledgement. This is the transmit buffer. And I need also a buffer at the receiver side. Okay, and this buffer at the receiver side will depend on the effective rate. So instead of multiplying by 24, I can use the effective data rate, which is 23.7 kilobits per second, if I want to be very accurate. Now, at 1 megabit per second, the numbers would a bit change. So the average data rate transmission would be 98.73%, which is going to be 98.7.3. The buffer must hold 1 mega times 0.48, which is 490. This is the similar number that we had before. Remember, for selective repeat, we need buffer at both sides. So there is a dramatic improvement in the data rate, but at the cost of requirement for numbering the blocks and also making sure that we have buffer size. That's basically it for the case of ARQ systems. You can try changing the numbers, and it requires you to focus, so please, you can stop the video anytime and make sure that you can reproduce these numbers. You can try repeating the examples for the case of 10 megabit per second, or even try to change some of the dimensions, like trying to do this for low Earth orbit and choose the proper delay accordingly. So please share your answers for the case of 10 megabit per second in the comment section. We'll see you then. Thank you very much.